Hi, in this lecture, we will be discussing the unsteady state material and energy balance. So the outline is that we will just do a general, the mass balance for the material balance for unsteady state system, so a general mass balance. And you have for unsteady state system for energy balance for unsteady state system. Okay, so for the material balance for unsteady state systems, so if you remember your general mass balance calculations in the previous lectures, we have mass in minus mass out plus mass generated minus mass consumed is equal to the mass accumulated. Now, so far we had only been doing steady states, whereas you have your mass accumulation as 0. So the whole equation is equated as 0. So mass in minus mass out plus mass generated minus mass consumed is equal to 0. That's for your steady states. Now, in the unsteady state, simply, still we are going to use the general mass balance equation, except that we do not equate this one into 0. So that is for unsteady state. You do have non-zero accumulation. So some sort of mass is accumulating in your system. So for your unsteady state mass balance, so another form of this equation, you have delta M. So that's the accumulation in your system that is equals to mass in over time, delta T, minus mass out over your time period, times the species generated, that's your product generated in your reaction, if you have a reaction in your bioreactor, minus the one that is consumed, the matter that's consumed in your reaction. So basically, if we can express this another way, so there's a change in the accumulation of mass. So there's a mass accumulated over time, so dm over dt is equal to mass in minus mass out, plus our generation minus our consumption. Now, going to energy balance. So if you remember your general energy balance equation, energy in minus energy out plus heat generated plus shaft work is equal to energy accumulated. So you have your again we have a non-zero accumulation. So again, you do not equate this one to 0 for unsteady states. Instead, there is a there's an energy accumulating in the system, or there can be a net energy loss in the system. So it's either a net energy gain or a net energy loss. So that's for unsteady state. So if you remember our general formula, that's the delta H of the reaction, the bioprocess reaction inside the reactor, and then this is the next term is for evaporative heat cooling, and then Q is the metabolic heat generation and your shaft work. So for steady state, it's equal to 0. However, for unsteady state, you do not equate this one to 0. So several assumptions must be made in unsteady state energy balance. So the system must be well mixed with uniform temperature and composition all throughout the whole body of the reactor. So that means you have a homogeneous system. So mixtures and solutions must be ideal, or you assume it to be ideal. And then you have heat capacities at the inlet and outstrips are independent of the composition and temperature. Hence, that doesn't necessarily change over time. And also, you have internal energy and enthalpy are independent of pressure. So here's an example of an unsteady state energy balance. Actually, I'm giving a solved example of that as handouts in your blackboard. So just wait for that. So that's it for this very short lecture. Basically, material balance and energy balance for unsteady state system is handled in the same manner, generally similar manner with the steady state system. The only difference is that you do not equate them to 0. You have a non-zero, or you have matter or energy accumulating in your system. So that's all. So see you in the next lecture.